So trusses were used in bridges in the past because it was the technology available at the time. They could go to a steel fabricator and get those pieces made, and then they could transport them to the site and build them. So it was a real practical way to get a longer span, but having individual pieces that are short enough you can transport them, and then with the equipment of the time, you can actually build the bridge.
Trusses are a very lightweight structure. That made them favorable for shipping. A lot of them were built in the steel mills, near the steel mills in Pennsylvania. This particular one, I believe, was built in Portland, but the steel probably wasn't made in Portland. And they still had shipping costs to get it down here. The members are all lightweight and they can be assembled with light construction. If you think about it, any person can put a truss together by just putting triangles together, and then the next triangle, and then the next triangle, and just build yourself out. That's oversimplistic, because one end of that triangle system has to be supported at all times. So these bridges that we did in Minneapolis, as we talked to the old folks, this was in '68, there were still some who remembered it being built in the 19th century. They said, well, those trusses were built off the ice. And so they actually just shored them up off the ice, as they built the truss across the river. Normally now you might build a small trestle to support the construction of the truss. But trusses are easy to build. We've actually have taken them apart and reassembled them. And you can see, once you've done that, you can see why they did it. Lightweight, easy to put together, doesn't take complicated ironwork, and they're very pin-connected truss was very easy to handle.
Typical truss analysis methods have changed over the years. When the Van Buren Bridge was built, it was all done by hand. When we analyze the Van Buren Bridge, it's using computer software. We'll do a 2D analysis of the truss, and then we'll model some elements for the truck to drive on, put those loads into the truss, but primarily now, it's going to be a computer model. The Van Buren Bridge was built in 1913, so it would have been people just grinding through calculations of allowable stress in each piece of steel and choosing the most restrictive load combination that piece is going to see. So it would have been extensive calculations, painstaking calculations, and those calculations would have been checked and rechecked.
The first step in designing a truss is to determine its configuration. This requires consideration of the function, physical constraints, loads, and environmental conditions. Much goes into this effort, and learning from an experienced engineer is the best way to understand the competing design requirements and arrive at an elegant layout. As we become more familiar with what makes structures efficient, we begin to see the genius in how the Van Buren and similar bridges were designed. Once we've established the geometry of the truss, we next find its loading. Recalling from Module 3, we found the forces at each panel point of the truss. This gives us the free body diagram of the system. With the free body diagram, we can now find the reactions at each support by first summing moments about the left side support. This causes the unknown support reaction to drop out of the equation, and we can solve directly for the right reaction. We can then solve for the left reaction by summing moments about the opposite side support. Finally, summing forces in the vertical direction gives us a valuable check on our math. In this case, the reactions are the same as the truss is loaded symmetrically.
I prefer analyzing using what we'd call the method of joints, which is taking it joint by joint and working starting out with the bridge reaction and working it ahead joint by joint, moving on with those loads down to the next joint. It's a very easy, intuitive way to look at a truss. You have to be careful that you've applied your loads correctly, or that you're keeping track of putting loads on as you move to joint. And it's labor intensive.
The method of joints is a thorough method that provides the internal force, either tension or compression, of every member in the truss. We begin by labeling each joint and give the member the name of the two adjacent joints. This method isolates each node or joint and applies two equations of equilibrium sum of forces vertically and horizontally. Because pins don't transmit moment and a point has no moment arm, we cannot sum moments. We can now begin our analysis by choosing the first joint to analyze. This requires finding a joint with only 2 unknown forces. Often the support joint meets this criteria. Let's start with joint A. This point has 1 known force, which is the upward reaction, and 2 unknown forces from member AB and AV. Because the only 2 forces acting in the y direction are the reaction force and the vertical component of force AV, let's sum forces in the vertical direction to find force AV. We can now sum forces in the x direction to find the force in member AB. We can repeat this process, moving from node to node along the truss, to find all the internal forces.
Method of sections is less labor intensive. You cut a section through the truss, and generally I use the method of sections when I'm trying to repair a member or understand a member and not have to move through the method of joints. I can cut the section and work just in that section.
The method of sections allows us to focus on portions of the truss that are of most interest, often the middle chords where moment is a maximum, and end webs and posts where shear is highest. To do this, let's create a free body diagram of the truss that passes through the middle. We cut only 3 members as we have 3 unique equations of equilibrium and can use the left or right side of the diagram. At each member we cut, we replace it with an axial force along the member length. We guess the direction of the force, remembering if we draw it in the wrong direction, we will simply get a negative number for the force. We will use sum of moments about 2 points, as well as the sum of forces vertically and horizontally, to solve for the internal forces of the cut members. We choose the points of rotation where 2 internal member forces intersect. Note one of these points of rotation often is off the free body diagram. Not only is this okay, it simplifies the solution. Let's begin by summing moments about point F. We get the following expression and find F sub RP equal to 511.6 kips. Summing moments about point R, we get and find F sub EF also equal to 511.6 kips. We can now sum forces vertically and horizontally to get F sub RF and use whichever direction we didn't use to check our work. Summing forces vertically, we see F sub RF is 0. 0 force members exist theoretically, but in practicality don't, due to unbalanced loading and secondary forces. Next, let's look at checking member strengths, utilizing the AASHTO LRFD bridge design specifications. We can do this now that we know the internal tension and compression forces in the truss. We first select the material we want to use for the structure. This will be a function of what material is available, its mechanical properties, such as yield strength, tensile strength, elongation, and fracture toughness, its fabrication characteristics, and its resistance to environmental effects such as corrosion. At the time this bridge was built, A7 was the most common steel used for bridges. It has an ultimate strength of 55 kips per inch squared and specified yield strength of half that.
Because to size a member in tension, you're going to look at the cross-section area, look at the load on it, and there's going to be a certain load per square inch of steel that steel can take, and steels come in different grades.
Let's consider 2 failure modes for a tension member: yield on gross cross-sectional area and rupture on net area. For the I-bar, the gross section is away from the pin, and net section through the pin. For a built-up section, the gross section occurs away from any rivet holes, and the net section through the rivet line. Once we know the material and gross and net areas, we can apply concepts we learned in mechanics of materials to find the tensile strength of the member we are considering. The first equation finds the yield strength of the member by multiplying a resistance factor by the yield strength and gross cross-sectional area. The second equation finds the rupture strength by multiplying a resistance factor by the tensile strength, net area, hole fabrication method factor, and shear lag factor. We take the lower of the 2 values as the member strength. If this strength is greater than the internal force, we can say the member is satisfactory. If not, we would retrofit the member in existing construction or choose a larger one for new. Note, this analysis doesn't consider fatigue, which we will cover in Module 7.
A member in compression, it's much more complicated than just a member in tension, because it can fail by being just crunched together, or it can start bending, and columns can fail, and different ways. And there's some long-established formulas for how slender you can make a part that's in compression. And you can go to a truss bridge and pretty easily just look at the members that are in tension and compression, because your tension member is going to have a much less cross-section than those that are in compression.
Buckling most often governs compression behavior, as members tend to be proportioned such that they will bow outward before the material can yield. Buckling occurs when a compressive load is applied to the end of a member. Slight imperfections in load and alignment cause the middle of the column to start to displace perpendicular to the long direction of the member. As the displacement increases, secondary forces occur which cause more displacement. This leads to higher secondary forces, eventually causing the member to buckle and potentially collapse. The geometry of a structural member drives how it will behave under load. Bending members are most efficient when they are deep compared to their width. However, compression members are most effective when they are more square. This is because the member will buckle about the axis with the smallest radius of gyration. Also, remember that as material is moved away from its neutral axis, the section becomes stiffer, stronger, and less prone to buckling. To predict compression member strength, we need to understand the effect of their end restraints. To do this, we apply an effective length factor, K. For a pin-connected column, like figure D, the K factor is 1. If we rigidly restrain the column, the K factor is theoretically 0.5, but we use 0.65 as no restraint is infinitely rigid. As we vary the end conditions, we see different K factors. The driving parameter in compression design is slenderness, which is the effective length factor, times the length divided by the radius of gyration. We use the smallest radius of gyration of the member, typically r sub y, but if the member had different bracing configurations, we may need to consider the two buckling directions of the member with their respective lengths. The AASHTO code limits slenderness to 120 for primary members and 140 for secondary. With all this said, we are now ready to calculate the strength of a compression member. We do this by first finding the nominal yield resistance, P sub O, and elastic critical buckling resistance, P sub E. The latter is the Euler buckling equation. If the ratio of these two numbers is less than 2.25, we use the nominal compressive resistance equation, P sub N, on the left. If it's greater, we use the equation on the right. We then multiply P sub N by the resistance factor, phi, and compare this against the internal compression force in the member. If this value is greater, the member has sufficient design strength. Looking at these equations in figure form may help us to better understand what is going on. If we plot buckling strength on the vertical axis and slenderness ratio on the horizontal, we see how strength drops as slenderness increases. In other words, if a member gets longer or smaller in cross-section, buckling strength decreases. We also see the Euler equation over-predicts strength for smaller slenderness values. In this video, we have begun to understand why structural steel trusses are so common. They are highly efficient and relatively simple to build. We have also explored two ways we can analyze trusses by hand, method of joints and method of sections. Engineers now use these to check computer models or for quick hand calculations. Finally, we have learned how to check the strength of tension and compression members. With a full understanding of these principles, you have the basic tools to design a truss.